All right, so we're going to take a look at inter and intramolecular forces. Please ignore all the background noises and sky. With that, intra means within. And when we say an intramolecular force, we are in particular talking about what is holding hydrogen to chlorine and HCl, and that would be a covalent bond. And we're not discussing bonding here. We're not interested in how these guys are attached. We're interested in how two or more of them interact, why they stick, why water is a liquid, why carbon dioxide is a gas, why sodium chloride is a solid, and what these are, solids, liquids, and gases that are have those properties because of the electron distribution and how great the charges are on each of these two elements. So what do I mean by that? So let's consider NaCl and magnesium oxide. Magnesium oxide, we remember, has a much stronger bond than sodium chloride, and it does that because it has greater charges. And as the charges go up, our bond strength or our bond energy is going to go up as well. And it's going to be harder to pull them apart, or they're going to stick together more strongly. If I threw in aluminum nitrate or nitrite or tride, excuse me, and I did these as they are, as +3 and -3, this would be extremely strongly bonded and very hard to pull apart. So as the charges go up, the bond energy goes up. Now, that's just two of these things sticking together. When we look at ionic bonding, it can be included in intra and intermolecular. And I know that's a bit sketchy. And in fact, it's neither because it's an ion, but it's a good starting point. So we're going to use it at the starting point because we need to compare complete charges with partial charges with temporary charges, because these are our options when we look at this. If we have complete charges, we have something that is ionic. It is very strongly bonded. It is a solid at room temperature. It's very hard to break apart if you just tried to heat it like on a stove and vaporize it. If we have something with partial charges, what we're looking at is something that is a molecule and that is polar. So when we say that something has a partial charge, what we're thinking about here is an electric dipole. Now, we know that an electric dipole occurs when our molecule is polar. We know how to spot a polar molecule. It either has two different ends, or inherently it's got lone pairs on the central. The only exceptions to lone pairs on the central being polar is for an expanded octet, which we're not going to deal with in this chapter. So again, polar. Polar means that our molecule is an electric dipole with a positive end and a negative end. And if you put two of these together, the positive end on one sticks to the negative end on the other, like two magnets would stick together. And this interaction right here, this sticking, is our in between our molecular, because we're looking at polar molecules, force, or intermolecular attraction. And we're trying to figure out what is going to be really strong and what is going to be weak. Well, again, this is kind of straightforward. As these charges go up, the strength of this intermolecular force is going to go up. So how do we determine nice, strong charges? Well, we're going to do it by electronegativity. So step one, we're going to ask, is it ionic? And if it's ionic and it's yes, it's going to have an ionic bond, and it's going to have very, very strong forces sticking it together. If the answer is no, we are going to ask, is it polar? And if it's polar, we have two options. We have a yes and we have a no. If we have a no, what we're going to end up with is a temporary charge. If it's yes, we're going to have one of these right here, and we are going to have a permanent charge. And our only job is to figure out how strong this permanent charge or charge distribution is on this molecule. Making sure when we see the word molecule here, we know that we are looking at something electrically neutral. And that means that it has no net charge on it. So we would be looking at H2O, and we would be looking at not, for example, OH minus. OH minus is ionic. water is a molecule. All right, with this in mind, if we have something that is polar and we have a yes here, it is going to have dipole interactions, meaning it's going to stick together because it's polar. Now, how strong these dipole interactions are depends on the atoms that are involved. So to look at the atoms that are involved, we've got a couple of things. One, the closer it is to fluorine, our atom, the higher the electronegativity is. The further it is from fluorine, the lower the electronegativity is. And the greater this distance, the more polar the molecule is going to be. But what we have is a really interesting case of dipole-dipole. So first of all, we're going to say, is it polar? If it is polar, we're going to say yes, and it's got dipole-dipole. But then we're going to ask, does it have HNOF? And we're going to do HNOF because it's a great and easy way to figure out our special case. This is simply a special case of dipole-dipole. And we're going to shorthand dipole-dipole as a DD. And special case means it's going to be a very, very strong case. Why does this occur? This occurs for two reasons. One, what we have is very, very small atoms, and we have a very large charge distribution. I want you to remember here that an ionic bond strength depends on two things. And again, we're looking at total charges, partial charges, and temporary charges. And the greater these charge distributions are, the more polar this is going to be, and the harder this thing is going to be to separate. So an ionic bond here, let's call it our bond energy, is going to depend on the product of the charges over the distance between them, the radius. So as the charges go up, electronegativity difference, or the size goes down, this temporary charge increases. And so when we have hydrogen, very small, low electronegativity, attached to nitrogen, oxygen, or fluorine, very small, high electronegativity, we are going to look at, in a sense, our very strong partial charge here. And that is a complete mess. And our partial charge is going to depend on this difference of electronegativities and the distance between. So if we have HNOF, hydrogen attached to a nitrogen, oxygen, or fluorine in a molecule, we have a special case of dipole-dipole. And our special case of dipole-dipole we call hydrogen bonding. Now, hydrogen bonding is still much weaker than an ionic or a covalent bond, but I'm going to put this structure in here on the bottom because it is relevant. This is an atomic force microscopy image, scanning electron microscopy image of this molecule. And what we see here is this spot right here, that. Now, with the note, that one is different than this one. These guys all here are covalent bonds. And we can see that when we go to the structure below, and we're just looking at these things that are holding our molecule together. But these guys right here, this is a hydrogen bond. Now, how is this relevant? Well, in this picture, on this image of this atomic force microscopy, this hydrogen bond is actually visible. This electron distribution is actually visible, indicating that this molecule has enough electron distribution that it almost looks like a real bond. Those are our hydrogen bonds, and what they are is a special case of dipole-dipole. What does it mean? It means it's weaker than a real bond. So it's weaker than a covalent or ionic, but it is still noticeable, and it has a dramatic effect on our molecules. So what are we going to ask ourselves? So we are going to ask ourselves as we go through here, if our molecule, if our species is ionic, okay? If it's ionic, we know what it's going to do. Is it polar? Yes. If it's got dipole-dipole, we have a second question. And our second question is, does it have HNOF? If it has HNOF in the molecule, it has a hydrogen attached to a nitrogen, oxygen, or fluorine, it is going to have a special case of our Dipole, this is our hydrogen bond, H bond for short, and that would be a yes. If it's a no, it is going to be just dipole. Hydrogen bonding is much stronger, and it has a dramatic effect on our molecules. So if we considered here our special case of this, and what we're looking at is hydrogen sulfide. We're looking at these guys here, and I want you just to ignore these two for a moment, and I want to just compare these guys and what happens if we go to and compare H2S to H2O. Both of these are in group 6. If we drew them out, H2O looks like this. H2S looks like that. So H2S is bigger, it's heavier, they are both polar, but one of these has dipole, the other one is going to have dipole, and a hydrogen bond. If you are asked which is the strongest, you're going to answer hydrogen bond. If you're asking for all of them, you would not only answer dipole, hydrogen bond, you'd also answer dispersion or London dispersion forces, and we'll get to that. What happens when you go from H2S to H2O? Well, this is what happens. And I'm looking at the boiling point. And if I look at the boiling point between H2S, which is minus 60 degrees Celsius, which means that H2S breaks from a liquid to a gas at a really, really cold temperature. But if I want to take water and break it from a liquid to a gas, that's my boiling point, it is at 100 degrees Celsius, which tells us that water sticks together much, much, much better. So why does water stick together much, much, much better? And the answer is that water's partial charges are much greater than H2S's partial charges. Why? Because of a greater difference in electronegativity over a smaller size. Shorthand, it has a hydrogen bond. So here, if we take a look at this and we start to try to rank them, we're going to say that anything with ionic bonding is going to be much, much higher. Let's just start with boiling point. And again, boiling point is going to be our temperature where we go from a liquid into a gas. If we have something ionic, its boiling point here is going to be much greater than something with a hydrogen bond, and that is going to be greater than something that just has dipole. Those would be its strongest intermolecular forces. Hydrogen bonding has dramatic effects on properties of molecules. If we consider, for example, DNA, and we look at our base pairs on DNA, our base pairs are going to have oxygens and nitrogens, and they are going to take a hydrogen bond. So how do we spot these? That's the question. The nice part is that we do not try to make this complicated. So if we want to take and consider, and we could consider H2O versus H2S, we could consider NH3 versus pH3, just for the sake of argument, and we're going to ask ourselves our questions. 1, ionic. The answer on these guys is no, not ionic. 2, polar. Well, in order to figure out if it's polar, you got to draw it. Well, we can draw these. We know that water looks like this. We know that H2S looks like this. And if we compare these, the answer to these guys is, are they polar? And the answer is yes, they are polar. And then we're going to ask the question, do they have a HNOF? Is there a hydrogen attached to a nitrogen, an oxygen, or a fluorine? Well, first of all, hydrogens never attach to hydrogens. So just by inspection, these guys have HNOF. And because these guys have HNOF, they are going to have a hydrogen bond, and they are going to have particularly strong intermolecular forces. They are going to have high boiling points, and they are going to be hard to separate. If we're looking at something organic or a bit more complicated, so let's just take a look at this guy. If we look at this one right here, first of all, we remember that with our CH2s, these guys are in the middle. And if we look at our OHs, remembering here our policy that for most organic compounds, and again, organic is hydrogens and carbons, you could have other stuff attached, oxygens, hydrogens, sulfurs, all sorts of stuff, but the carbons and the hydrogens are the important parts. For these guys, carbon has 4 bonds. This is going to give us our nice 0 formal charge. Nitrogen, 3 bonds, 1 lone pair. Remember oxygen 2 bonds, 2 lone pairs. If we went to group 7, they have 1 bond and 3 lone pairs. Why is this relevant? Because if we take and we tack the oxygens on the end, first of all, how do you know the oxygens are on the end? Because we wrote it like that. We're not trying to be mysterious. If we write it like in some direction, making sure you obey the octet rules, you're going to get the shape looking like that. If we put our hydrogens on, they're going to go down here. Our carbons have 4 bonds here. Our oxygens, we know, want 2 bonds and 2 lone pairs, which are going to look like this. And if you look at this molecule right here, you can see that 1, it's polar. It's not ionic, it's not a metal with a nonmetal. 2, it has HNOF. And you didn't even have to draw this to see that it had HNOF. It has the OH. So inherently with that OH at the end, it has HNOF, and this is going to have hydrogen bonding. And with the note, the more HNOFs something has. So if I compared, for example, H2O versus H2O2, H2O2 has 2 HNOFs, OH on each end. H2O just has 2 OHs, not that mess of oxygens in the middle. The more possible places we can have our HNOF, the greater the intermolecular forces. So the more HNOFs it has, the greater the intermolecular forces. Which leaves us to the last possibility. So again, we know what we have. We know that we have ionic. We start with that. Yes, ionic bond. No. Is it polar? If it's polar, it's either going to have dipole or a hydrogen bond, which leaves us to this guy, nonpolar. Well, the issue with nonpolar stuff is it still sticks together. If we have iodine, for example, iodine is a solid at room temperature. And we think about that, RT room temperature, it's a solid at room temperature, which means it sticks together. And so it's like, why does it stick together if it doesn't have charges? The only way 2 things stick together is that we have a positive on one and a negative on the other. We have to have charges. And what we're going to go here with this one is we're going to go to our last kind of our intermolecular forces, which are London dispersion forces or an induced or temporary dipole. And we're going to explain it like this. We're going to say, okay, imagine or know that electrons are in constant motion. If we have, for example, helium sticking with helium, and you can liquefy helium. It's weird when you do, but that's a different story. Helium, we know, has 2 protons, 2 neutrons, and 2 electrons. And if we think about these guys sticking together, which at some point they truly will, you have to get them really cold, but they will. If we think about our protons, and I'm just going to do those for neutrons and these for my electrons. If I've got my protons here and my neutrons, my electrons, we know are waves. We know that these are in constant motion, and these are out here somewhere. And I'm just going to take and sort of draw them in. Well, they're in constant motion, which means at some point, so imagining these electrons are in motion, if I have a second helium over here with its electrons, and if our electrons are there, these guys are just kind of going to ignore each other. So we've got to imagine they're cold, so they're getting nice and close together. And we're going to think about the fact that our electrons are in constant motion. So this force in between these is temporary, and it is incredibly short-lived. If we imagine that these electrons right here just shift over, and they're at some point, they're going to be over kind of on the same side. And if we take and imagine that these electrons are going to be like this, what we have now generated is this atom, it could be a molecule, where it has the nucleus as the partial positive and these electrons as a partial negative. And this one here has its nucleus as a partial positive and these electrons over here as a partial negative. And it is the nucleus of one pulling on the electrons of the other that are going to give us this temporary and very small dipole on this molecule. And we say it's induced because it's in fact the nucleus of one that pulls on the electrons of the other and kind of pulls it into this asymmetric shape and makes it charged. And what we have here are what we call London dispersion forces or dispersion forces. We frequently shorthand this as an LDF, London dispersion forces, or just DF. Both of these answers are fine. And if we take a look at this, this is our last possibility. And our last possibility is whether or not it is polar. So if it is nonpolar, for example, our iodine, I2, it is going to have London dispersion forces only. So how do we rank these? Well, again, we rank these with our step 1, ionic, much greater than a hydrogen bond, which is going to be greater than a dipole-dipole, which is going to be greater than our London dispersion force. Now, this is under one set of conditions, and our set of conditions here is going to be similar molar mass. If our molar mass changes, how this uneven distribution of electrons occurs in our London dispersion force can change. And our London dispersion forces, LDFs, depend on molar mass. Molar mass, one way of looking at that is the trend in molar mass is going to be the same as trend in radius of our atoms. The bigger the atom is, for example, if I compare fluorine to chlorine and then go down to iodine, iodine is much, much bigger than fluorine or chlorine. The bigger it is, the heavier it's going to be, and the looser the electrons are. And as the electrons get looser, it becomes easier to pull this temporary dipole. So our London dispersion forces depend on molar mass, and as the molar mass goes up, the London dispersion forces are going to go up. So what are we going to do? We're simply going to look at these guys right here. Is it ionic? Is it polar? If it's polar, does it have H0? If it does, it's hydrogen bonding. If it's not polar, then it's going to have London dispersion forces only. And with the last note, anything with electrons is actually going to have London dispersion forces. They become relevant when they're heavier, but if your question on Achieve asks you, list all the intermolecular forces, you're going to need to include London dispersion forces even on something like water. So here, when we say that our glycerol molecule here, this has a hydrogen bond. If they wanted the complete set of intermolecular forces, we would say that this has a hydrogen bond, which is a special case of dipole-dipole, and you would include that as well. And it would have London dispersion forces or dispersion forces, and it's going to depend on the question. All right, with that in mind, the question would then be, how does this affect the molecule?